Welcome back everyone to this second lecture on energy transport by radiation. So based on your feedback, this is more useful than just reading the notes, so I will carry on and make a few more screencasts like this. Let me know if I should change my pace or any other things that can improve. So the topics for today is that we will extend the theory that we developed last time regarding black bodies, and we will look at so-called non-ideal or real bodies today, so how radiation behaves in real-life settings. In that context, it's important to discuss Kirchoffs' laws of radiation. These allow us to relate different non-ideal properties of the surfaces we are studying. Following that, we will look at gray bodies, and gray bodies is a semi-idealization. It's an approximation that we will use quite frequently. It's better than assuming that the bodies are black because it includes some of the non-ideal phenomena that we're looking for. But it's still an idealization of reality. Finally, we will look at a practical application of Stefan Boltzmann's law, Planck's law, and Wiesen's displacement law, together with the laws of Kirchhoff, look at the principles of a pyrometer, and that's how you can use radiation to investigate temperature. So we're continuing with the compendium, so that's still our source. We're jumping to chapters 3.3 and 3.4, which we will cover today. So, as I mentioned last time, we introduced some laws that describe so-called black bodies. And a black body is a surface that has the ability to absorb all incident radiation and emit all possible radiation. So this is a benchmark that allows us to absorb as much as possible and emit as much as possible. If we refer to the figure that I introduced in the last lecture, shown here, we see that we have some factors that relate, for instance, the external to reflected radiation. And that particular relation is given here. We have the total external radiation, GI, and we have the reflected external radiation, rho I GI. And this factor rho is a non-ideal effect, which we will investigate in detail today. The additional effects or factors we'll be looking at is this emissivity epsilon I and the so-called absorptivity alpha I that we have here. And we should also take note that we have a reflectivity here as well, which is the same for both radiation leaving the system and being emitted towards the surface. So we have a sort of internal mirror effect of the surface for radiation trying to leave the surface. So that's the topics for today. And we start with the non-ideal bodies. Most important point is that real surfaces are not black. And the parameters that we've just discussed, the absorptivity alpha and the emissivity epsilon, describe the relative blackness of a real body. And it's a non-dimensional number that has a value between 0 and 1. If alpha and epsilon equals to 1, the body is black. On the other hand, if alpha and epsilon are equal to 0, then the body is white, which is the opposite of a black body. It will reflect all incoming radiation. There is an additional parameter which is related to the ability of a material to transmit radiation. This parameter is called the transmittivity, and we use the symbol tau to describe it. But in this course, at least for the moment, we will assume that tau equals to 0. So we will only consider what is happening on the actual surface of the material. One parameter that we will consider and spend quite a lot of time on is, however, the reflectivity, rho. And reflectivity has a definition given like this. It's 1 minus alpha, where alpha is the absorptivity. That means for a black body, for black bodies we have alpha equals to 1. That means that rho equals to 0. Which is in line with our definition of the black bodies, as the black body will absorb all possible radiation. It will not necessarily reflect anything, so it has to have a reflectivity of 0. So we will use these parameters to describe how the mathematical formulas for radiation emission will be. Particularly, we will start with the total emitted radiation. And the total emitted radiation is EI, and that's given by epsilon I, which is the emissivity, times symbol here EBI. And EBI is simply sigma times the temperature of the surface to the power 4. And that's the total radiation emitted from a black surface with an equivalent temperature of Ti. So if the surface were black, it would emit this amount of energy. But since it is a non-ideal surface, it will have a emissivity which is greater than or equal to, smaller than or equal to 1. That means that the total emitted radiation from this surface will be smaller than what you would have gotten from a black body with the same temperature. So that's Stefan Boltzmann's law for a non-ideal or real body. Moving on, we have Planck's law. And Planck's law tells us that the radiation is distributed over different wavelengths. You remember we had some specific peaks in energy flux for the given wavelengths corresponding to different temperatures, and based on that we could say that, well, a body with this and that temperature heated to that specific temperature will glow in a specific color. So for Planck's law, we found that the same black body energy flux, or emitted energy flux, is given by the integral of the density of, or the flux density of radiative, the radiative flux density, the integral of radiative flux density over all possible wavelengths. So if we want to do the same thing for a non-ideal body, we will introduce a epsilon lambda which is the so-called spectral emissivity. And this spectral emissivity accounts for the fact that a surface will have an emissivity that depends upon the specific wavelength. This means that some surfaces may be very good at emitting, let's say, green light, but bad at emitting red light, for example. So in order to determine the total radiation emitted, or the radiation flux emitted from a non-ideal body, we will again do the integral over this spectral density for a black body, but we will use the spectral emissivity as a weighting factor. We then split up this integral and have this average value on the outside of the integral, and this average value represents just epsilon and is the average spectral emissivity over all wavelengths. So this is a simplification. We do the average over all possible wavelengths to simplify the formalism. What we have here in the integral, the final part of the integral, is the same as we have in Planck's law itself. So that's just the integral over the spectral density over all wavelengths, and we weight it again with this average spectral emissivity to get the radiation from a non-ideal body. In the same way, so this was the energy that was emitted, we will have to do a similar consideration for radiation which is absorbed. So if we look at the absorbed incoming radiation, we write this just as a flux here. The actual flux which is absorbed is the absorptivity of the surface, alpha I, multiplied with the irradiation, Gi, which is the total incoming radiation. This total incoming radiation is also in principle distributed over different wavelengths. So this one also should follow Planck's law. But we should note that this comes from external sources. Then, completely analogous to epsilon, we introduce a average absorptivity which equals to the average spectral absorptivity. So this is important to note when we are discussing these epsilons and alphas, and thereby also rhos. These represent average values over all wavelengths. That means that your system may perform slightly better or even much better than the average for specific wavelengths, but it may also perform much worse than the average for specific wavelengths. So make sure to check this before you start coating your surfaces with something specific, because you might get a nasty surprise. Another important point to note is that epsilon, the emissivity, or then the average spectral emissivity, if you want, of your surface, is a function of two things. First point is that it is a function of the temperature of the surface itself. So in this table we have specific temperature ranges for different materials, different substances that have different surfaces. This is then the total emissivity. So it's a function of the temperature. Also, as I spoiled, it is a function of the surface properties. Here you can, for example, see for aluminium, we have two tables here for aluminium. One is a oxidized surface, the other one is rolled. They have different temperature ranges, but they overlap at least. And we can see that the oxidized surface has a epsilon between 0.2 and up to 0.33, while the rolled product, that's aluminum film if you want, is 0.4 to 0.06. So that means that they have a very low emissivity. And this one is a moderate emissivity. We see that the whole range of emissivities is used for the different materials that we are using in our industry. One important point is that these refractory materials typically have a quite high emissivity. Same is true for these, call them rocky materials, that have a high emissivity compared to the metals that we have here, that typically have lower emissivities. If we consider the absorptivity, however, so the absorptivity is more complicated. And the reason why it is more complicated is that it depends upon the properties of the absorbing surface, of course, and the properties of the surroundings. And of course it doesn't depend only on that, it also depends upon the temperature of the surroundings, because that's where the radiation comes from. So you have to remember sort of the history of or the origin of your radiation in order to treat it correctly as it arrives on the surface. So the absorptivity the absorptivity alpha is then a function of the surface properties and temperature of your surface and the properties of the surroundings and the temperature of the surroundings. And since rho equals 1 minus alpha, that means that the reflectivity also is a function of what is going on around your system. That means that you have to adjust your values or specify your values of alpha and rho for a specified source of radiation. Small note on optics before we move on to the laws of Kirchoff. Specifically, I want to highlight the difference between diffuse and specular reflection. Specular means mirror-like. So this would be a polished metal surface, for example. While diffuse means the opposite. It's dull or matte or not shiny. The difference between them is quite important, because if you have a specular reflection, you will have an incoming ray of light, and that will be reflected with a given outgoing angle. So this is theta incoming and theta outgoing, And this is typically what you see in high school optics. If we have diffuse reflection, then your incident ray will come in like this, but it will scatter radiation in all directions. This is the radiation that we will typically consider in this course, just so you know. So, we move on to the radiation laws of Kirchoff. And as I mentioned in the introduction, these give the relation between alpha and epsilon, or between the absorptivity and the emissivity of the surface. We start with the so-called monochromatic formulation, and that tells us that, well, the monochromatic emissivity of a body, we call that epsilon lambda, so it's for a specific wavelength, is always equal to the monochromatic absorptivity at the same temperature. Of course, these are temperature dependent properties. So Kirchoffs law tells us that epsilon for this specific wavelength equals to alpha at the same wavelength, lambda. That means that if your body or your surface is an effective absorber, or let's say red light, it will also be an effective emitter of red light. So this is useful for a narrow band of the spectrum. However, for engineering purposes, we are normally looking at this total emissivity and absorptivity, or the average ones if you want. And then we need to be a bit more careful in our formulation. So for a total emissivity, the total emissivity of a body at a temperature T equals to the total absorptivity, alpha, from a black source of radiation with the same temperature. That means that epsilon equals alpha, so the average ones equal each other, as long as the temperatures are the same. Also, the radiation has to come from a black source, as I mentioned. So this is, of course, a limitation that we have to make for this assumption to work. But it's, of course, very practical when it works, because then you don't have to consider all of the properties of everything surrounding your body, which, of course, can be quite tedious to do. We do, however, have a sort of simplification which is in between, and that's the simplification relating to gray bodies. Gray bodies will give us the following nice features. So first, if we assume that we have some surface for which epsilon lambda equals alpha lambda equals a constant. If this is the case independently of the wavelength, then of course the average value, the average spectral emissivity and absorptivity will be equal as well, independent of the source of radiation. Since this is so useful, because it gives us very greatly simplified formalism for both absorbing and emitting of radiation, we define these bodies, so bodies that have epsilon equal to alpha equal a constant, as being gray. So, to recap, black bodies, they have epsilon equal to alpha equal to 1. White bodies, they have epsilon equal to alpha equal to 0. Real bodies have epsilon as a function of lambda and alpha as a function of lambda, while gray bodies have epsilon equal to lambda, and they are both somewhere between 0 and 1. But they are the same and they are constants. And this will be our go-to assumption for the rest of the course. Not only is it a very useful approximation, it's valid for most surfaces that have diffuse reflections. So this will work badly for highly polished metals, but it will work very well for instance, refractory materials. So in the following lecture, we will start to do some more detailed calculations on what happens when you have gray bodies in next to each other that emit and absorb radiation. But before we do that, we will visit some measurement techniques, or a measurement technique to be more specific, which is radiation pyrometry. And a radiation pyrometer is a non-contact temperature sensor that infers the temperature of an object by detecting its thermal radiation. So essentially, you measure a flux of energy, and you use Stefan Boltzmann and Planck's law to then tell us something about the temperature of the object that emitted this amount of energy. There are three different implementations, at least three to my knowledge. We have a total radiation pyrometer. We have the optical pyrometer, and we have a two-color pyrometer. And we will look into the details of each of these at the end of this lecture. We'll start with the total radiation pyrometer because it's the simplest one, thereby also the cheapest one. And the total radiation pyrometer will determine the black body temperature. And the black body temperature is the temperature of a black surface with the same total emissivity as the surface we are measuring. So same total emissivity as the surface we are measuring. We'll see what that means in some equations a bit further down. So what we will use is a relation between the true temperature, T, so that's the actual temperature of the surface. Use that in red in the following. And the black body temperature, which we'll call TB, which we'll color in blue. Both of these are then assumed to be given by Stefan Boltzmann's law. So what we do is that we measure a flux, as I said, of energy coming into our instrument, and we assume that the temperature follows or comes directly from a black body, or the energy flux comes directly from a black body, while it in reality comes from a surface that has a emissivity, so that's a non-ideal surface. These two are then assumed to be equal one another. That means that we set the pure black body emitted energy equal to the weighted emitted energy, then weighted by this epsilon. For sigma is a constant for both of the sides of the equation, so that those cancel. And we get the following relation between the true temperature and the equivalent, or not equivalent, but the measured black body temperature. And it scales as 1 over epsilon to the power 4. This means that TB will always be smaller than T. So the temperature that you are measuring, that your sensor gives you based on the flux, will then always be smaller than the actual temperature of the surface. So let's do a very brief example. Let's say that your instrument gives you a reading of 1500 Kelvin. If your surface then has a emissivity of 0.5, then the corresponding true temperature would be 785. So almost 300 Kelvin higher than what your instrument gave you. If epsilon, on the other hand, is 0.9, then the error is just 40 kelvins, which is not that bad. And as we see, epsilon becomes, or the error becomes smaller and smaller, the higher the value for epsilon. That is, the closer you get to a black body. Because if your surface is a true black body, then epsilon, of course, is equal to 1, and both these two equations become equal to one another. The second technology that I would like to discuss is the optical pyrometer. The optical pyrometer determines the so-called brightness temperature. So this is again the temperature that the instrument gives in its display. This temperature is the temperature of a black body which emits the same radiation quantity within the wavelength lambda up to lambda plus delta lambda as the body we are measuring. So the total radiation parameter, as we had here, that's sort of based on just applying Stefan Boltzmann's law. So we have a measurement that assumes a black body, and we then have the true surface, which is a non-ideal surface, while in the optical parameter it's something similar. We again measure a flux of energy, which is then assumed to come from a black body, while it in reality comes from a non-ideal surface with a different temperature. Now, since we are looking at the radiation within some specific wavelength, this is determined by Planck's law, because that's what Planck's law gives us. So we simply put in the distribution from Planck's law in the left-hand side and the right-hand side. The only difference between these two is then, of course, that here on the left-hand side we have the true temperature of the surface, while we on the on the right-hand side we have the true temperature of the surface, while we on the left-hand side have the temperature that shows up in our display. And on the right-hand side we also have this emissivity, which follows from the non-ideality of the surface that we're trying to measure. A lot of things here are constants. For example, this constant a will cancel on both sides, as will lambda to the power of 5. And if you reorganize these fractions, you get the expression that we have here, just by inverting the fractions. Now we'll introduce a few numbers. So this constant that we have called b is Planck's constant multiplied with the speed of light divided by Boltzmann's constant. And it takes the numerical value of 0.01439 meters Kelvin. I'm sorry. While we have to make some assumption on lambda, the wavelength, let's say that it is around 1 micron for visible light. If you put in these numbers, you get that this exponential function, and this one, so to speak, takes this value. It's around 15,000 divided by the temperature. Now, if you have sort of a reasonable temperature, means reasonably low, the exponential function of 15,000 divided by your temperature will in all cases be much greater than 1. And that means that if you compare the exponential term here and the exponential term here, you can drop this minus 1 and this minus 1 because of this. So that means that our expression becomes quite much more simple. We only have now the exponential function equals the emissivity for that specific wavelength times again an exponential function. We can solve this by taking the logarithms, bringing us here. And as we know, epsilon lambda, that is the spectral emissivity, will always be smaller or equal to 1. And this will result in Tb lambda, so the temperature that we are reading off the instrument, again, will be smaller than the true temperature of the surface. Have a look at this one if you don't trust me, but it is the case. So let's do a example again. For this example, we need to specify the wavelength we are looking at. So we do this for visible red light. Note that for the visible red light we are at 0.667 micrometer. So that means that the approximation that we did here is even better, because here we assumed 1 micron. So if we assume that we have visible red light, we again look at a reading temperature of 1500 kelvins. If the spectral emissivity at that wavelength is 0.5, then the true temperature is 1575 Kelvin, while if we go again to a higher emissivity, the error is smaller. And the error is smaller for both of these cases compared to the total radiation pyrometer that we looked at previously. Of course, you can always correct on your instrument if you have knowledge of the emissivities of the surfaces you are measuring. You may have seen that if you have an infrared thermometer at your home, which is useful in these days, then you can select what kind of surface you're measuring, if you're measuring a wall or if you're measuring a body, and that sort of corrects for the emissivity within a given range. That will even give you a better estimate, of course, if you know the emissivity of your surface. The final technology that we will discuss is a two-color pyrometer. And the two-color pyrometer determines a third parameter that we call the color temperature. Again, we'll use a blue-colored temperature, TC, for this property, or this temperature. And this is then the temperature of a gray body. It gives the same ratio between the emitted radiation of wavelength lambda G and lambda R as, again, the surface we are measuring. So this is also related to Planck, because we are looking at specific wavelengths. This we expect again to be better than the total radiation pyrometer that only considers the whole spectrum at once. So we are looking at the ratio between the spectral density at the lambda G and lambda R for a gray body compared to the emitted energy of the true body that will then be weighted with a spectral emissivity for lambda G and a spectral emissivity for lambda R. So we plug in Planck's law directly, and we get this relation with the exponential functions, etc. Constant A cancels directly, but take note that in the first iteration, at least, the wavelength do not. At least they don't cancel from the numerator and denominator, because they are different wavelengths. However, they are the same wavelength on both sides of the equal sign, so ultimately they will cancel, so this whole fraction cancels against this fraction. If you look closely, you will get the following relation if we again apply the similar numerical approximation that we are looking at wavelengths of the order of 1 micron. So visible light. So this is the simple relation. The temperature Tc is essentially what we measure, and the temperature T is the true temperature of the surface. So if we now look at an example again, specifying a lambda g to be green and the lambda r to be red, and we then look at the same temperature as earlier, 1500 Kelvin. And we now need to know the spectral emissivity in the green part of the spectrum and the red part of the spectrum. So we need more parameters in order to do this. So if we have a epsilon or emissivity, spectral emissivity for red light, which is smaller than that we have for green light, the true temperature would be 1419 Kelvin, which is smaller than what we measure from the pyrometer. However, if the spectral emissivity for red light is greater than that we have for green light, then we measure something which is larger than the temperature that we read off will be smaller than the true temperature of the surface. Then we have a very neat feature related to what we have been discussing, which is that of a gray body. Because a gray body, as I said, body which is truly gray, will have the same emissivity. So they will have the same value, it doesn't matter what value they are, but it will be the same for all wavelengths. If that's the case, if we look back at the expression, this one becomes 1. And what we then have that equals to 1, and of course this doesn't matter. Then we see that we get that the temperature that we measure is exactly equal to the true temperature of the surface. So the error in measurement will actually be 0 in that case. And as I mentioned, many of the materials that we will consider that have sort of diffuse reflection, particularly refractory materials and these things, they have quite well described by gray body theory. And that means that we very accurately can measure their temperature also with this specific method. That's it for today. Hope you learned something and enjoyed it. And you'll get a new lecture from me sometime next week.